Chapter 5 review, we're looking at exponentials. That's what it's all about, right? So we given this exponential, we're asked to graph it. So we plug that into our y equal or y1 equals, plug that in. We notice that that's a positive. All right, so we should know that it's going to face up, right? It's going to keep on growing. So this one kind of faces up right here. This one faces up right there, as well as this one faces up. But we know that when this is larger than 1, that it's going to be an exponential growth. So that means it's this one. Okay? So our domain, we can plug in any number, any x to our left, any x to our right. So that'd be all real numbers. Right, so this one is a decay, and while this one is a growth. Right? But we can plug in our calculator, set our domain and our range, or our x's and our y's, right, our window. We can see that the range would be everything below 0, but it kind of looks like it hits 0, or everything above 0 kind of looks like it hits 0, right? Well, we know if we look at this asymptote, right, we know that if anything's being added to that, that is our asymptote. Well, nothing's being added, so that would be y equals 0 is our asymptote, which means our range is everything, since our graph is facing up, everything above 0, right? So it would be all positive numbers. Or it's always f of x, your y values are greater than whatever that asymptote is, the asymptote there, okay, which ours is 0. That's why you can say positive real numbers as your answer. Okay. Now, what's the y-intercept? Where does it cross the y-intercepts? That's 0, 1. So 0, 1, and we already said what our asymptote is, what's being added to at the end, or where does our graph not cross? What do we approach but not cross? Y equals 0. Okay, here in number 3, we're looking at where or do we have an exponential decay? So that means somewhere in between 0 and 1, correct? My base is something between 0 and 1. And so here we got 0.5, that's between 0 and 1. 3.5, yes, that's a fraction, but 3.5 is 1.5, right? And 10 over 11, that is less than 5. 1.01, even though it's barely more than 1, it is more than 1, so it's going to grow. And this negative just flips it and makes it look like this, right? So it's not a decay, because it is not between that base. It's not between 0 and 1. That base is 2. All right, looking at number 4, we have Eric running, and he runs for 20 miles each week, and then he plans to increase that total by 5%. So 5% increase, right? So he's going to run 5% of 20 is 4, right? But he's not going to run 4 miles the next day. He's going to run 20 plus 4, right? So we got to add that. And so this is where it comes back to that formula that we have our principal times 1 plus our rate, right? Raised to n, how many times we're going to do it for, right? So it's 1 plus our rate, and our rate is 0.05. So it's 1 plus 0.05, so 1.05 is our growth rate. 1.05. And you could figure that out saying, okay, he's going to run 4 miles, but we add 20, right? So we have to add 20 to that. Well, if I factor out 20 from both these two terms, right, when we get 20 parentheses 1 plus 0.05, which is our 1.05. And that's all they're asked for, is the growth. And we could put this in an equation by just putting n here, and we could do the 8th week or the 10th week or whatever it is to find our total distance that he's running, right? All right, example number 5. So you got to think back, to section 2, I believe, where we're solving, or section 3, one of the two, where we're solving exponential equations, right? So we got an equal sign, so we're saying this left side equals this right-hand side. So, but these are not the same base, so we need to turn 4 into something, and we need to turn 8 into something, but we want to do it using exponents. We want to say, what number raised to an exponent, and I can use that same number raised to a different exponent to equal 8, right? So that'd be 2 squared is 4, but 2 cubed is 8. So I could rewrite this 4 as 2 squared, and since this 4 is being raised to 3x minus 1, so is this 4 right here being raised to 3x minus 1. Sorry, 3x minus 1. Now, this 8 is being raised to the same as this 8, x plus 4. So 2 cubed is being raised to x plus 4. Now what do I do when I raise powers to powers? I multiply, right? So 6x minus 2 powers to powers, so that'd be 3x plus 12. Now, since the bases are the same, and we're saying that the left-hand side is the right-hand side, we can then say the exponents have to be the same. So 6x minus 2 has to equal 3x plus 12 if this statement is true, right? So then we can go ahead and solve this, subtract 3x, or you can just think about it and figure out what the answer is, that's fine. Add 2 to both sides, and so we get 3x equals 14 divided by 3, and so then we get x is equal to 14 thirds. And I would normally check this, plug it back into my original x's, and see on a calculator if I'm correct, if the left-hand side equals the right-hand side. But since it's a fraction, I don't want to do it. But there's your answer. Okay, on number 6, we're asked to graph this equation, both of these equations. Let's graph them. And we can see those graphs right here. And we want to know, okay, well, where's the solution to this equation equaling this equation, right, when they're set equal to each other? Well, that we just know we put 1 as y1 and y2 for both equations. Okay, so put y1 and y2 for each equation, right? Maybe not both equations, that's y1, y2. So one equation is y1, the other equation is y2. And then we go ahead, we don't even have to hit graph, we can graph, but we can do a second trace. Hit second trace on our calculators and look for that, move over to calculate, and then go down to intersect. Right, so we want to see where those two graphs intersect, and there would be our solution right there, that point of intersection. Okay, this question here, number 7, we are looking at Paula investing $1,000 at 1.6% interest, but it's compounded monthly. So when we're compounding monthly there, we want to use a compound interest formula, but because it doesn't happen continuously, and it doesn't just happen once a year, we are going to use this formula. A equals our principal, our amount in the account equals our principal, times 1 plus our rate over n, how many times we compound in a year, raised to how many times we compound in a year, times t, how many years we do it for. So nt really represents how many times it's compounded over the life of the either the loan or the investment. Okay, so we want to know our principal. That is 1,500, or not 1,500, let's read the problem. It is $1,000. So we have $1,000. I keep wanting to write 1,500. $1,000, 1 plus our rate, but our rate is 1.6%, so that'd be 0.016%, right? I gotta move that decimal over twice from that 1.6. And then over how many times compounded? It's compounded monthly. Well, how many times is that in a year? If it's monthly, that'd be 12. Raised to 12 times how many years we do. It doesn't say how many years, right? So we put as t as in years. Now what they say is, they say after how many years, so they actually want to know what that t is. Well, the value of the account, so how much is in the account, will be 1,500. So we set this equal to 1,500. Now what we can do is two things. Set this as y1, and then set this as y2. And then we can see where they intersect, just kind of like that last question, right? And we can go in our calculator, make sure we adjust our window. So our window might have to be maybe set, our y value might have to be, it's going to get 1,500, right? So maybe put it at, 1,400 to 1,600, right? But our x is the hard thing, right? We could start out at 0, because we're not going to have negative years, and maybe do 10, or maybe adjust it from there, right? If you don't see it crossing, then you can adjust it. I think maybe 20 to 50 probably will work for your x's. And then you can hit graph, and then you can do second trace, go over to calculate, and then hit intersect. And then you can also, another way to do it is just look at the table and see where this y2 is equal to 1500 for your y1. So you could also do that too. You could look at your table. And so we look at that table and we see that on that we get about 25 years, and it says round to the nearest tenth, so that'd be 25.4 years it's going to take in order to reach that 1500 amount that we want in our account. Okay, on number 8, we want to solve this one. It's very similar to number 5, except for we have this inequality. The only time it switches, inequality changes when we divide or multiply by a negative. So any inequality, if it's facing the other way over, it's or equal to, it also changes when we divide or multiply by a negative. Okay, so here we want the bases to be the same. We have 3 and 27. Well, can I rewrite 27 as a base of 3? Because that already has a 3, right? So we say, oh, 3 times itself 3 times is 27. So I could rewrite this 27 as 3 cubed. And this 27 is being raised to 2x minus 3. So this 27 has to be raised to 2x minus 1. 2x minus 1. So now when we do is powers to powers, we multiply, so we get 6x minus 3. Now that those bases are the same, now we can set those exponents equal to each other. 5x, I guess not equals, less than 6x minus 3. Okay, and then I can solve this. Most likely, if you don't want to flip this, all you have to do is just take the smaller amount of x's and always subtract it. Sometimes you have to do a little more work, right? I have to move this over. So then I have 3 is less than x. So that's my answer. But notice that my answer blanks here, they come in a little bit different way. The x is always first. Well, my inequality is opening towards the x. So I need to make sure when I write this, my inequality is opening towards the x. So these are saying the same thing. X is greater than 3. 3 is less than x, right? So make sure these answers are always the x comes first. So if you have your answer like this, I need to make sure that inequality is opening towards the x on this problem. Or if it's opening away, I make sure it's opening away when I write my answer. Okay, so those two are exactly the same thing. Okay, number 9 here, just dealing with powers of exponents when I have a product. So two things being multiplied by each other, and they're raised to a power. I can take that power to each of those two things. So I can take 7 to the power of 2, and I can take e to the 3x to the power of 2. And then what do when I have powers raised to powers? I multiply, right? So this is e to the 6x, and then 7 squared is 49. So I don't take 7 times 2 because this is an exponent and this is not an exponent. So I got to take this 7 and raise it to the power of 2, which is 49. All right, so 10 and 11 kind of go together. All right, they're based off this same function right here. E, which is button on your calculator, second ln, is raised to x minus 2 plus 1. So I can enter that in and see what my range is. Right, I can look and see what value is it approaching but not actually crossing. Well, I can also look at what's being added to at the end, and that's always going to tell me what that asymptote is, right? Now I just need to know, okay, am I going up with my graph, or am I going down with my graph, or am I going like that, right? So here we notice that because it's E, which is 2.7-ish, something around there, it's positive, right? There's no negative in front, so I know this is a growth because E is bigger than 1. So then I know I'm going to be bigger than 1, which is right here. Okay, but you can graph it and look and see. You can even go to a table and look what values is it getting close to, but it's not crossing. Now we can look at the same graph and say, okay, as x approaches, right, as I look from it from the left, right, as it says, this means as I look at my graph to the left, what is it doing? And here are y values. F of x just means y. Means y, means s, means y, means y, right? What's my y value doing? Well, it's approaching that asymptote, right? It's approaching 1. Now this means, it means to the right. So as I go to the right, what's my y values doing? They're just going up, right? So at positive infinity. So those two are your answers. Okay, on number 12 here, it's just asking us to write the equation of f of t. So f of t for how much are we going to make in our investment after t years or after so many years, right? So it wants f of t. Now this one, it says it's continuously. So anytime you use the word continuously or compound continuously, this is the equation because it's just collecting interest repeatedly, second after second after second. Okay, that'd be principal times e, that e button in your calculator, second ln, raised to an exponent of r times t, your rate times your time in years. Well, our principal is $2,500 we're investing, and then e, and then raised to our rate, but that is a percentage. We want to change that to a decimal, so 0.085, and then times t, which we don't have, is just t. Right, and there, that one is done. Okay, number 13 is just asking if it's geometric or not geometric. To be geometric, from our sequence of numbers from one number to the next, we have to be multiplying by the same number each time as we go along, that common ratio. It could be division, because division is the same thing as multiplication. It's just multiplying by the reciprocal, right? So how do I go from 10 to 5? I divide by 2, or I multiply by half. Well, can I multiply 5 by half? That's 2.5, and then 2.5 times another half is 1.25, so that is geometric. If it's adding repeatedly the same number, that's called arithmetic, not geometric. Okay, so here 1/3, that's being multiplied by 4/3, and 4/9 multiplied by 4/3 is 4/27, or 16/27. 16/27 multiplied by 4/3 is 64/81. This one, our r equaled 1/2. Right, so that's geometric too. Now this one, 1 times 4 would be 4, but 4 times 4 is not 9, right? So that's not multiplied by the same thing. So that is not geometric. Okay, 2 is being multiplied by 1 each time, but in order to be a growth, right? A growth, that means to be greater than 1, right? Greater than 1. And that's multiplying by 1 is just keeping the same thing, right? That's just a horizontal line, right? If we're asked to graph it, there's just a horizontal. So this is not. Okay, this one's just asked which one is geometric. Okay, so this is just a line, so that's linear. This is kind of almost looks like a line. Okay, this one kind of looks like an exponential, right? And this one kind of looks like an exponential here, so it's probably between these last two here. Okay, so what I can do is really just find my y values. So this y value is just above 0, can't really tell. This one's kind of above 0, don't really know, but this one right here is a 1, right? It's a 1. This one is a 2. This one is 3, 4. And this one's 5, 6, 7, 8. I'm just looking at the y values. It's just like a sequence of numbers, just like the other problems were, right? So how am I going from 1 to 2? Well, I multiply by 2. Is that the same thing as this? So from 2 to 4, multiply by 2, and from 4 to 8, multiply by 2. They have the same thing, so it's got to be this one. This one's a little bit off. It goes from 1 to 3. So I'd have to multiply by 3, right? But the next one, if I multiply by 3, I should get 9, but I only get 4, 5, 6. So that's not the same, right? Multiply by 3, but then multiply by 2. Has to be the same multiplication each time. So it'd be that one. Okay, number 15, this is a way to sum up numbers, this sigma notation. So sigma notation. Sigma means to add or get the sum. I'm adding numbers in my sequence. Now this right here is our explicit equation for any number in the sequence, right? That tells me any number in the sequence. I believe that was a sub n equals a sub 1 raised to r raised to n minus 1, right? In that section. That's to find any number in our sequence, right? So this is just saying add up add up all your numbers in your sequence, starting at the first number in your sequence, all the way to the 10th number of your sequence. So it's pretty easy. We're just going to use this sum formula. So I want to sum up, add up, starting with my a sub 1, the first number I'm adding in my sequence, not necessarily the very first one, so not necessarily this one. Okay, minus a sub 1 times r raised to n all over 1 minus r. Now, what's nice is whenever we start at 1, the bottom number, if the bottom number is 1, then our n equals always the top number. Okay, and our a sub 1 will be what's next to the in between here. A sub 1 would be in between the sigma sign and the parentheses r. So a sub 1 is just a sub 1. And then we need our n, which is the top, and we have our r. R just stays r the whole time. So r will equal r. Okay, so then we can just plug those in. So s sub 10 equals a sub 1, which is 2.5, minus 2.5, r, which is 3, and our n, which again is the top, is 10, all over 1 minus our r, which is 3. Now, I can just plug that in a calculator. If I want that fraction, I just hit alpha link. So I hit alpha link, and I enter that in there, and I get 73,000. Okay? The only tricky part is when k does not equal 1. When it does not equal 1, then my n is the top number of the sigma. So the top number of the sigma minus the bottom number of the sigma, and then I just add 1 to that. Okay, and that will be my new n that I plug into this formula right here for n. Okay, and then a sub 1 is kind of the hard part. Whatever k they give me, k equals some number. Okay, I should put an equal sign here. So whatever k number equals, I got to plug in to the explicit equation. Okay, so sometimes that's hard to understand. So let me give you just a quick example, right? So instead, let's start this off at, we go from 2, and we just want to go to 5 of this same equation. Okay, 3 raised to k minus 1. Okay, so here, if I want to start at 2, that means in order to find my a sub 1, that a sub 1 is not going to be 2.5. Okay, I have to plug in this 2 minus 1. 2 minus 1 is 1, and then 3 raised to 1 is 3, and then 3 times 2.5 is 7.5, right? So my a sub 1 for this problem, my a sub 1 would equal 7.5, and then my n would be the top 5 minus the bottom number 2, all over, and then yeah, those are my numbers. So then I can just plug it in. A sub, oh, I gotta add 1, sorry. So that would be 3, and then plus 1. So I get my n equals 4. So s sub 4 would be my new a sub 1, 7.5, minus 7.5 times my r, and the r is the same, raised to my n, which is 4, all over 1 minus 3. And then I can hit enter on that. So whenever k does not equal 1, I have to find out what my a sub 1 is by plugging it into the equation. I don't have to solve a sub 1, I just plug it into my equation. A sub 1, whatever your r is, raised to k minus 1. You just enter in that k. There'll be numbers here for a sub 1 and for r, and you hit enter, and whatever you get, that will get your a sub 1. Okay? So it's a little confusing, but it's just the case when k is not equal to 1. Alright, here we have students experimenting. They decide they have 3 students want to start a rumor. So those 3 students, they start a rumor and they tell 2 people each. So that means they get to 6 people. So 6 people are the first ones to hear it. And then they tell 2 more people each, right? So that'd be 12. And then they tell each of those 12 tell new people, right? These are all new people that haven't heard it. So that'd be 24. And we want to find, okay, what is the total number? So that'd be S sub n, total number of students who hear the rumor. So these 3 people are not included in the total because they are the ones that started it. They didn't hear it. They just came up with it. R and raised to n all over 1 minus r. So we need to find our a sub 1. Well, those are the first people that heard it. So a sub 1 would equal 6. So 6 minus 6, and our r, what are we doing each time? We're multiplying by 2. So our r equals 2. And we raise it to n. Well, how many times are we doing it? At the 8th day, right? So on the 8th day, we plug that in. And all over 1 minus our r again, which is 2. So then we hit enter and we get a total of 1,530. So we get a total of 1,530. And so that's the formula for S sub 8, right? Total amount of people who hear the rumor by the end of the day 8. Okay, and then I think in the answer key it's actually 1533. So what they do is they just add these three back in. Okay, so if you have any questions about reading this problem, doing it, okay, you can come to my desk and ask me, right? But they asked the total number of students who hear the rumor, so that's why we started out here as 6. But they should have asked for maybe total number of people that know the rumor would be, I would think that would be better wording, would be 1533. But we used the people that hear it first as the people that first heard it was our A sub 1. Okay, so that was the difference between this 1530 as your answer and 1533. They added the people that started it. Okay, so you can always come and ask me about that if you have a question like this on the test. Where do you want to start, you know? Okay, number 17 here. All we're doing here is we have a list of t's, times, and we have a list of maybe heights. I guess it doesn't say what it is, but we have our x's and we have our y's. So here I'm going to go to stat, and I'm going to go to edit, and I'm going to hit enter, and I'm going to enter this into my L1 and this into my L2. And then what I can do is from there is just make sure my go to second y equals and make sure stat plot is on. Stat plot on. All right, so then you hit enter, and then you turn on your stat plot, make sure that's highlighted, X list, make sure that's L1. If it's not L1, then you can hit second stat, and you can choose L1. Then do the same thing for L2, except for you want it to be L2, or your Y list to be L2, and then you can go ahead and hit graph and see what that looks like, and that is an exponential function. Okay, if it's linear, it'll look like line. If it's a quadratic, then it's going to look like a quadratic, like a U. Okay. All right, number 18, very similar. We do the same things as this one. Enter this L1, enter this L2. Okay, the only difference is after we hit graph on this one, we can see what it looks like, exponential, linear, quadratic. So once we can identify it as linear, exponential, or quadratic, then we can go ahead and say, okay, since it's exponential, looks exponential, then I can go ahead and hit stat, and I can move over to calculate. And then I want to go down until I get to number 0, which says exponential regression. Okay, and I can hit enter there. And then it asks me for my X list, my Y list, and then it asks for frequency, which you're going to just leave blank. Frequency, leave that blank. So make sure this is your L1, second stat if you need to. And then L2 is that one. And then down here, next point, it says store regression equation. This one you don't need to necessarily do that, but I'll show you how. Okay. So store regression equation allows me to store as a y equals, and there I hit vars. I move over to I hit y vars, and then I hit function, enter, and then I can select y1, and it will store that, and then I just move down and say calculate. Calculate. And then I can go, after that I could hit graph, and it'll graph these points just like number 17 did, but it'll also graph this equation that you just stored in there under your y equals, so then you can use it to make predictions. Okay, but here we don't need to do that. We don't need to do the store regression equation. Okay, all we need to go down is to calculate, and it's going to give you, since we did an exponential, it's going to give us an a and a b raised to x. Okay, now this a and b is probably a whole bunch of decimals that they give us, right? So we just want to round it to the hundreds place. So we find our a, which is 2.7, and our b, which is 1.53. And again, it keeps on going, but they just round it to the hundreds place. And then, so we're looking at an exponential equation, and that on there is the only exponential equation. If it was a quadratic, I would go down to quad regression, which I believe is number 5 on my calculators. Or if it's linear, I would go to linear regression, which I think is number 4. Okay, but this was an exponential, that's why we went down to exponential regression. And since we're just asked to come up with a formula, we can go down to calculate. But if I want to enter that in, which I think was maybe one of these problems that we had to do, that would be the next one. Okay. So for that one, we're good here. right there. Okay, so let's go ahead and do the next one. So on number 19 here, we're going to do the same thing as we did on 17, 18, L1, L2. Okay, we don't necessarily need to graph here. We can if we want to. And let me make a comment. If you're making it a graph, you might have to adjust your window, right? These would be your X's, these would be your Y's. So just like on the last problem, you might have to adjust your window if you're looking at a graph in order to fit your X's and your Y's on there, right? So here, what I can do, put that in there. Don't necessarily have to put push graph. What I can do is go over to stat, move over to calculate, go down here. I mean, you can look at it, see if it's exponential, but this says exponential on there. Okay, I think looks like the answer key, I don't think they did an exponential. I think they did a quadratic. So your answer is going to be a little bit different. In the answer key, it says 186.6, but I believe I get an answer of 183. And this is from a quadratic, and this one right here is from a exponential. Okay, but they say find the exponential function, so that's why I used exponential and not quadratic. Okay, so going on from there, stat calculate, go down to exponential regression. So you might want to graph this to then see if it maybe it does look like a quadratic. So let me go ahead and graph that real quick and see. And a little sidebar, if you want to clear your calculator out your L1, L2, just highlight L1 and hit clear and hit enter. Go over to L2, hit clear and hit enter, and it'll clear those for you. Yeah, so I did this, and it looks like an exponential, so that would be your number at approximately 11. So you go to calculate, move over to hit stat, move over to calculate, go down to exponential regression, and then in your X list, make sure you have L1, and Y list, make sure you have L2, second stat if you need to change it, and then frequency, leave it blank, and then store regression equation. There you're going to hit vars, move over to Y vars, and then go down and hit function, hit enter, and then you can type that into your Y1 or Y2 or whatever, and then you can go to second table or second graph, which is table, and then you can go down to year 11 or year 11. I guess go down to 11 and see what it is, and that was 183. So that is how you can do that. But yeah, that's supposed to be an exponential function. I'm not sure why they wanted a let's see, I'm doing the other one right now. Let's see, at year 11. So exponential, yeah, that gives me 183 for that one. So I did the quadratic, and it's not that. Oh, I remember what this was. Okay, so let me show you real quick. So you can do that. Now, if you look at your y equals on your y1, notice that it's 3.64586 and keeps going, right? They want those to round the coefficients of your basis to the nearest hundredth, right? So it actually wants these hundreds. So it wants me to stop right here and do 3.65 in my y equals. And then my R is 1.423. It wants to round to the hundreds, right? So you got to round those ones. So here, you might not want to put this as y1. You just might want to go down to hit calculate. So leave that blank. You can leave the story question blank, and you just hit calculate, and that will tell you what your A and B are, and then you can look at your A and your B, and then you can round it to the hundreds place right here, and then you can go ahead and put that in your y1 as that raised to x. So leave that as your y1, and that's where they got this 186.6, where our 183 is actually probably more accurate than this 186. That's why they have this word approximately there. So sorry about that one. Yeah, make sure you read through the equations. Anytime you got a question, come up and ask me. And then notice when you do hit calculate on that, it gives you an a and a b, but it also gives this r squared. And so when I look at that r squared, I want that r squared to be closest to 1 as I can. It will probably never be 1, but I want it closest to 1 as I can, the r squared. Okay, the closest to 1 as possible. So when I do an exponential regression, or I do a linear regression, or a quadratic regression, I want that r squared to be closest to 1. And that's, the closer it is to 1, the best fit it is, the strongest it is to recognizing that model, right? So if I look at these, which one's the strongest? The ones that's closest to 1.99. So C is the strongest, then 0.96, and then 0.83B. Okay, and that is your review for Chapter 5.